Hi, my name is Bill Kinney. This is part 2 of a math series I'm doing on large and small numbers, scientific notation, accuracy, and precision. In the first part, we looked at a long problem that looked like this. In March of 2012, there were about 313 million people in the United States. How precise is the number? How accurate is it? Write it in scientific notation and put it in perspective. We saw that the precision was indicated by, in a sense, the number of significant digits as well as the description of the number as being in millions of people. So this was precise to the nearest million people. We didn't really know how accurate it was because we don't know the true number of people precisely, exactly. But if the method of obtaining the number is good, we might imagine that this is rounded to the nearest million people, and therefore we're probably accurate to within 500,000 people. And that's a reasonable estimate for the accuracy, and as a percentage, we can do this to calculate the percent that we are, in a sense, likely to be off, about how accurate it is likely to be. Now that might not be right, again, because nobody knows the true value of the population, and it changes almost from moment to moment, but this is ballpark probably if the method of obtaining the number is fairly trustworthy. We also wrote the number in scientific notation. 313 million people is the same as 3.13 times 10 to the 8th. 10 to the 6th is a million. 10 to the 7th is 10 million. 10 to the 8th is 100 million. So 3.13 times 100 million is 313 million. Wanted to do some calculations with a different kind of calculator in this video. How would you represent this number in this kind of calculator? Well, you could type it in as a 313 million, and it will display it to you that way as well, although it tacked on a decimal. If you wanted to enter it via scientific notation, with this type of calculator, you would really need to do the 10 to the 8th power first. I press the Y to the X button to get the exponent. And, okay, actually it's not in scientific notation there, but that is 100 million. Multiply that by 3.13, and you'll get the number. Now, if I multiply this by some humongous number like, a million, probably it's going to give me the answer in scientific notation. And there you see it. It is in scientific notation. What this means is 3.13 times 10 to the 14th. Now you don't see a 10 here. You don't see an E like you did on the other calculator either, but there is a space there. It means 3.13 times 10 to the 14th. And then you can continue doing calculations with this. You can now multiply it by, say, 854 and get another number in scientific notation as 2.67302 times 10 to the 17th. That's the way this calculator represents numbers in scientific notation. We put the number in perspective by figuring out how long it would take you to shake everybody's hand. If it took you 5 seconds to shake each person's hand, and again nod at the person, and then go on to the next person. And it would take you about 50 years, we saw. And realize that that's also assuming you are shaking hands constantly day and night, never sleeping, never eating, never doing anything else. Of course, if you're doing all those other things, it's going to take you longer than 50 years. New question. A typical virus might have a diameter of about 100 nanometers. And we've got similar questions here. How precise is the number? How accurate is it? Write in scientific notation and put the size of this number in perspective. And here I'm not saying how to put it in perspective. I'm just saying put it in perspective and leaving it up to you, in essence, to decide how you want to put it in perspective. All right, precision. You write the number like this, 100 nanometers. Don't worry about what nanometers means at the moment. The implied precision here is based, again, on the number of significant figures. There's only one significant figure when you write it like this, unless you say specifically that the 0 and the 0 there are significant. Zeros that follow a non-zero number and are before any decimal without a decimal being written are assumed to not be significant. Therefore, there's only one significant digit here, that first digit. And so as far as the precision goes, that we would say this is then precise to the nearest 100 nanometers. If I had written, say, 150 nanometers here, then I'd have two significant digits, and it would be precise to the nearest 10 nanometers then, because I'd have the 10 spot having a non-zero digit. And again, that would be assumed to both be significant if I had 150 there. How accurate is it? Once again, I don't know how accurate it is, exactly, or precisely, because I don't know the true value. And in reality, different viri, is that the plural of viruses? Viruses, probably not viruses, different viruses have different diameters. And so you really can't say how accurate this is unless you have a specific virus in mind. And let's just pretend we do have a specific virus in mind that happens to be, let's just imagine we know exactly it's 127 nanometers. Let's imagine that being the true value. So if we imagine that as being the true value, then the accuracy in absolute terms would be 100 nanometers, and you can abbreviate nanometers this way, minus 127 nanometers, the measured value, or the estimate, minus the true value, negative 27 nanometers. Now here I guess I'm pretending this 100 is maybe precise to the nearest nanometer, but that's the idea about how to find the sometimes called the absolute size of the error, telling you how accurate it is, and the measured value or estimated value in this case is below the true value, and therefore this is a negative quantity. As a percent, you'd take the negative 27 nanometers and divide by 127 nanometers, the true value. And if I did that on this calculator, let me just do 27 divided by 127. And oops, something's wrong there. 27 divided by 127. There we go. And that, as a percent, is about 21%. Negative, and so I get a negative 21% here, indicating that my measured value is too small. Again, this is pretending I know the true value. Now, in reality, nobody really knows the true value, and so this is kind of hypothetical, and it would depend on the particular virus that you're looking at. But for the sake of argument, we just pretend the true value is 127 nanometers. How do you write it in scientific notation? This is a very small number. Nanometers is very small. A virus is very small. In fact, a nanometer is a billionth of a meter. 1 nanometer is 1 billionth of a meter. 1 divided by 10 to the 9th, really. 10 to the 9th is a billion. So 1 billionth is 1 divided by 10 to the 9th, and that can be written with a negative exponent, like that. And this would be the number of meters, actually. 100 times 10 to the negative 9th meters is the same as 100 nanometers. In a sense, the 10 to the negative 9th is the nano part of that unit right there. This is not the traditional write it in scientific notation. It is traditional to have just one non-zero digit before you have a decimal. So I'd have to move the decimal, imagine moving the decimal place to the left 2 spots. And if I do have just one significant digit, I would just write it as a 1 there. And if I'm moving the decimal spot to the left to go from here to here, then I need to add 2 to the exponent. Negative 9 minus or plus 2 is negative 7. So 100 nanometers is the same as 10 to the negative 7 meters, really, which would be essentially 1 10,000,000th of a meter. I think what I'm going to do as far as putting this number in perspective is wait for the next video, since this one is already at 10 minutes. So we'll look at that in the next video.